I'm going to talk to you guys about robotics a bit, about what I spend my life doing. Specifically, and I speak kind of, a lot of this will come from a different context. I too was he showed pictures of the DARPA Robotics Challenge. I too was sitting on the stage, or in the stands, completely embarrassed to be called a roboticist, unfortunately. We basically watched millions of dollars of robotics, which could have been beat by a dizzy 8-year-old easily. And so essentially this kind of, I guess, speaks to a lot of the reason why I do what I do, right? Is the fact that I think there's holes in the game plan that we currently have. So specifically, I founded Rome Robotics. We make exoskeletons. For context, just so you guys can follow, those of you who don't know, exoskeletons are worn robots. Think Iron Man. Now that you're thinking that, remember that that's a comic book, so back it down a bit, right? But that genre, right? It's worn robotics. So about me, provide a little bit of context. There's a leader in this field out there selling exoskeletons, kind of leading devices out commercially. It's Exobionics. So my background, I was one of the first employees there, and I was a lead inventor of their products. Whenever I talk about this and kind of give the background, my wife always brings this magazine off our shelf. We had a subject who they were taking a picture for, and he didn't show up. And so I was voted the most paraplegic among us and asked to stand in. The hilarious thing then is for the next 3 to 4 years, I was the only person who knew how to use the device, me and one other person. And so we were there all the time, and every time we walked in, people were like, "It cured you! Oh my goodness, it's amazing!" I was, much to their chagrin, I was never a paraplegic, so I was simply standing in. But then I oversaw long-term research there, really with the goal of how do you make exoskeletons a reality? How do you actually fulfill on the dream? And then after about 6 years of that, I left and I founded Rome, and we are off making a new type of exoskeleton, which I'll talk more about when we get to it. So the purpose, and this is really the purpose of the whole community, right? This isn't just me. This is everybody who's making exoskeletons. We're building exoskeletons to live in everyday life, right? Everyday life is why you build exoskeletons, because it's not good just to fill this one little niche here and there. You really want to go with people. You want to do things that they want to do, whether it's in their daily life, in their work experience, on the battlefield. There's lots of applications, but everyday life is key. It's not an afterthought. It's kind of the reason we invest. If you look at the broader opportunity, I like to look at it as a landscape. Whether it's where you live, where you work, or where you play, there's opportunities in a number of these places. And really, you can just let yourself dream a little bit about it, right? Wherever your body creates the limitation. You can't hike over that next hill. You can't run faster. You can't lift that extra box. You have rehabilitation issues. You have lost the ability to walk. Wherever the body becomes the limitation, this is where exoskeletons present an opportunity, a unique opportunity to go solve those problems, right? To go with the person. And so this is really the promise of exoskeletons. It's what we all dream of. Unlike regular robotics, you show a robotic arm, and you have to get people to dream with you a little bit, right? They see a hunk of metal in the corner. You talk to people about exoskeletons, and I spend most of my career asking people to stop dreaming for a second, right? Because immediately they're like, "Oh, this is going to help me dunk a basketball." One day, not today, right? But it's really easy to believe in this promise. And the promise is that there's going to be power with you when you want it and where you want it. It's going to go with you into your life and kind of be there as you're out there doing it. I think where the problem with this is that we have fallen short. I say we very purposefully because I, to be honest, am as much culprit as I am solution. All right, I've stood right with these people and made the generation of devices that exist out there today. We have fallen short of this promise, and in a number of areas, right? So healthcare is a perfect example. The promise is there's 2.7 million people out there with the after effects of stroke, right? You hear those numbers and you think about the real lives. That's not just a statistic. Those are real people. There's 12,000 paraplegics annually in just the US, and these numbers are on the order of 3x as you scale through other kind of predominant countries, EU, Japan, things like that. So there's lots of people out there who have this who we dream we can help, right? The problem is we're making devices that really only fit in an inpatient rehab center. We're falling short of that promise. This, by the way, this is Exo, so this was my baby for a long time. It learned to walk when my son learned to walk. And so I love it like a child. The problem is it's a $100,000 machine that weighs 50 pounds. We would always dream about the story of sending these home with people, and then you kind of forget the reality that it's more expensive than most people's cars. And outside of the microcosm of the Bay Area, it's more expensive than most people's houses, right? This is a big issue as actually getting this to people. And so we've fallen short of the promise. We still discharge people in wheelchairs. Other areas, you look at industrial assistance, everybody just looks at the numbers and say there's $15 billion a year spent on direct workman's comp claims for overexertion. That's, again, a huge number. Real lives, real people. And what we're making is we're making exoskeletons that while they feel like they check the box, that picture right there, this is a device from Lockheed Martin, probably a class leader in this space. That's a 20-pound tool. So if you think of what's going on here, they've built a 60-pound exoskeleton to put around your body to help you hold a 20-pound tool. It's kind of an interesting concept because what you really sit down and you think of, really what they've done is they've built a scaffolding. It's a movable scaffolding for your body because it's not an exoskeleton, right? Because the concept of an exoskeleton is power when you want, where you want it. This is going to be in one place because it's going to be in the place you stand. Well, really what you're offering someone is you can stand still better with this device, which there are roles, there are places where that's really helpful, but that's not the promise. That's not the dream that we've laid out. And I think with all of these, with Exo too, I don't point these out as failures, to be honest. I point these out as successes. These are the people that are winning in this space. And both of these last two devices, I designed. This device in particular, the predecessor to it, I designed in my team, and then it was licensed out to Lockheed Martin. So I've seen these things. I understand the decisions that are made. Like I say, I'm the culprit here. The situation continues. You look at performance enhancement. This is actually where a lot of the money is going into. Money gets poured into this space through research, a lot of it through the DoD. The goal is that you're going to make Iron Man, right? The promise is that you're going to be able to run faster, jump higher, run for longer, lift more, which is a really cool thought. I think we all really dream of this thought. But as of today, there are only 2 devices in the world ever, 30 years and $300 million worth of research, 2 devices ever that can make you do anything other than stand still better, which is an amazingly sad statistic for my entire career path, right? Building robots and specifically building exoskeletons. The only 2 devices, too, when you sit down and you look at them, they are devices that make you walk, slow walk at lower energy. And I think the number is about 6% less energy. So you spend 6% less when you're walking at 2 miles per hour, and the only 2 devices that can help you when you're not standing still. Again, we are falling short of the promise, right? Really, my industry creates expensive exercise equipment, which is sad. So again, I didn't cherry pick. There's lots of areas where this is the case. You can sit down and you can look through these, and if you want, I'm very willing to have a detailed conversation about any of these applications. I kind of thought of the high level of what these applications could look like, and off the top of my head picked which they were. Are they cost limited or weight limited? The reality is almost every single one of these markets are cost limited and weight limited, so it's really a this or that kind of question. There's a lot of things out there that we want to do, but there are these barriers, right? And so what I believe is you still come back to the that we have fallen short of this promise. And this isn't a doom and gloom. I am extremely hopeful about where these things go. I think there's so much potential. But I think we have to recognize where our limitations are. And so unlike a robotic arm, right, the video was shown earlier of the KUKAs, unlike a robotic arm, it can sit one day in a dark room and it'll move boxes, and all of us will be extremely happy because it's done something of value. You'll get a mobile base, and the mobile base will move things around at night while everybody's gone home, and we'll feel like there's value. Exoskeletons are a different animal, and the economics are accordingly are different as well. They're only as good as the number of people you can put them on. Literally, they will only scale with people. So you can't make the argument of, well, it's this many shifts, it's this many people. No, you make one device for one person, and that is how it will work. You could hit a few extra shifts, but it's one device for one person at any given time. And that's how these devices will work. And so what we have to do is we have to make exoskeletons that can support that. And this is where I think we've missed the point. The solution to that is a device that people can afford and integrate, right? And it's kind of obvious if you think of the promise. The promise is it has to be with you and can go where you want it to go. You have to be able to buy it to make that happen, and you have to be able to take it with you in the process. But this is what we're missing. We're missing devices on the cost and weight side that can really be a part of our actual lives. So what is the problem, right? What are the limitations? And I think this is the thing, and again, I speak to this device as a success. Understanding the problems is a key first step. A lot of people like to say it's power, and power is a thing. I completely agree. It's a challenge I deal with on a daily basis. But often people say what you need is the arc reactor, right? I need Iron Man's blue chest thingy. I would take it. If one of you have it, great. Give me a call afterwards. I would use it in a heartbeat. But the devices that are out there today, power is not my problem. If you gave me Iron Man's arc reactor, I've actually solved, say even something better than that, a magic power source that solves, it's zero weight, and it does all the power. I've only solved 20% of my problem. The majority of the exoskeleton is actually not power, it's robot. Robot is my problem, not power. So this is kind of where we started at a fundamental level, is what's the issue driving this? So when you think of costs, the devices like these, and this is not an exo-specific thing, this is robots in general. The costs are driven by the fact that there are a huge number of parts in these actuators, right? Thousands of unique parts when you look at a standard robot. In addition to that, the majority of the parts are almost all high tolerance manufactured, right? Everything is custom machined plus. Everybody says plus or minus 5 thou is like your normal tolerances. That's pretty precise. And if that gets met, the reason that's the case is because there's lots of forces, and these things destroy themselves if they get out of whack. And in addition to that, all of those kind of lots of parts, high tolerances, lead to service burdens. And so the costs of these machines get out of whack really quick. In addition, on the weight, as I said, it's not governed by power. And ultimately, when you see a heavy system, it significantly limits how mobile you can be with the machine. So what we started to look at is what are our other options. So here's when you look at materials, we use steel. This is kind of the going standard for engineering as your go-to material, especially if you want to go to a strong material. Aluminum's on there also, but it's a smaller bar, so it's been omitted. When you look at this, specific strength is something I'm going to talk about a little bit. And specific strength is how strong you are compared to how heavy you are. And so what you see is steel is a useful material. Definitely is. Don't get me wrong. But there's other materials out there that are better specific strength. There's more strength for less weight. And so what we set out to do is say, how do you leverage this? There's something to take advantage of here. And really what you look at is you look at it on a broader scale. This is metals. This is what our 150, 250 years of engineering experience has been honed to understand, is how to design with metals, this sliver of the world. But there's a lot of stuff out there that is not that we don't really know how to use. And I'm not saying that these other things are always the solution, right? Things like nylons and carbon fibers and plastics and things like that. I'm not saying they're always the solution, definitely not. But what I think they are is I think they're not in the toolbox for most people who have built robots before. And because they're not in the toolbox, we aren't actually solving the entire problem the right way. We're solving it with some subset of solutions. So this is what we're doing. We are building a new type of exoskeleton that is centered, instead of around metals and motors, they're centered around fabric and air. So essentially, these are structures predominantly made out of high-strength fabrics, which we use air to turn those high-strength fabrics, the shapes that we make, into structures that provide torques on your body, right, and actually create motion. What it leads to is extremely lightweight. extremely low cost, and high performance systems. So you can all imagine the lightweight. Our primary materials are going to be plastics and high strength fabrics, right? These things are lightweight, easy to get to. Our manufacturing techniques are predominantly sewing and injection molding. The two cheapest ways we know as humans how to make things is pretty much what we're going to rely on. And then in addition, the high performance. Now the high performance one, I'm the first one with you. When I started this effort, I thought we were a little crazy because that was the one that scared me the most. It doesn't help us to reduce cost and reduce weight if we're also going to give up capability. What our problem is that exoskeletons for the last 15 years we've been making, where the cost and weight don't justify the capability, we need those to be in balance. So we can't give up on the other side. And so this is, and you can actually see a picture of it down here in the bottom left corner. This is a perfect example. This is a device that we recently did for a Department of Defense project. You can see it here. It's going to move around a little. This is about a 20-pound system all in. It doesn't, for complete openness, this doesn't have a compressor. This is a gap in funding for this particular device. And so this runs in a lab. This is it moving around. Without compressor, about 20 pounds. With compressor, will be about 28. This device, actuation at the ankles and at the knees, plastic structures. This is entirely made for augmenting performance, so allowing people to run faster, jump higher, run for longer, things like that. You can see here, this is what moving air, we built custom valves, custom pneumatic infrastructure to move air down into the actuators at the given time. It's coordinating with what it's seeing the human doing, right? It's sensing the phase of the gait and the behaviors of the person, the intended motion, and identifying, are they attempting to walk, are they attempting to run, are they attempting to stop, and then coordinating the behaviors accordingly. This is a system that we have running and operable. For us, it's really, really a very cool thing because this system is the first system in the world that we can make people run faster when you put on the device, and we can lower the metabolic burden of running. So we can actually send you out there and we can have you run for less energy. Again, 30 years of research, $300 million, no one has ever come close to these capabilities. And this isn't, honestly, I think the thing here is not to tout what we're doing necessarily. We just, I believe, are an example of what the solution needs to be. The solution for robotics needs to be us to recognize where the limitations are and learn the lessons. So the details of exoskeletons are really, really complex, and I would love to talk numbers with anyone who cares, but the concept is really simple. Weight is bad, and power is good. So when I can add more power for less weight, I can do good things to the human body. So where these systems primarily have their advantage is the fact that I can provide 10 times the power for the same amount of weight as a conventional system. Right? And actually, when you look at those two systems that I mentioned are the ones that can make you walk faster better, or walk at a slow speed better, our ankle assemblies are about half the weight and about 5 times the total power capacity. And so that's the reason why you can go make things that let you run as opposed to just things that let you walk at a slow speed. So then on my side, I think the immediate question is what's next, right? Like where are these windows that devices like this make sense? If exoskeletons are going to reach the promise, how do you leverage it? How does it actually become something? And so back to the array of options, I think for us what we've looked at heavily is kind of the intersection of where there's an actual market. Right, because again, I talk about the paraplegics and I talk about stroke victims, and these are wonderful spaces where we can do a lot of good. But you think of paraplegics, for example, there's in the US completely saturated. Every single year there's 12,000 a year. There's very few, if you're going to sell something that's a few $1,000s, you're not going to make a viable business off selling that with a handful of patients, essentially. And so what you have to do is you have to find markets that are large enough to justify the effort, the volume that you can now leverage by making exoskeletons in a different way. Similarly, you need. I'm a big fan of selling into places where people spend real money and not chasing luxury items. And then capability, right? We're not selling Iron Man. Probably never, to be honest. But in the near term, we're definitely not. And so where can we find those places where those kind of three things, feasibility, viability, and our technology, our capability line up? And so what we're starting to look at is kind of this middle set of capabilities when you look across this live-work-play spectrum, rehab or fall reduction in populations that have limited or impaired mobility, but outside of facilities, pushing things into homes, letting people again take it into their life around them. Repetitive lift safety, so industrial spaces where people are that 15 billion number, where people are moving and lifting boxes and are straining their body in ways that are significant. And then ultimately into the home, creating things where you can hike farther and you can run farther and you can experience the world in a way that you can't currently. I believe these are possible options for exoskeletons. And so again, I think that the whole thing to think about here is we are simply one alternative that is developing high specific power actuators, or exoskeletons. There's no one else who's demonstrated capabilities like this because no one else is making actuators of the specific powers that we're talking about. But I believe there's other solutions out there. 10, 20 years from now, someone might make some new kind of motor, that's fine. I'm not necessarily saying that this is the only solution. I think this is the best solution that we have right now. But what we're learning is that robots need to change the way we think about the problem, right? And so I think this is what I want to take away is that the promise, it's possible. We don't want to sit there and hear that we haven't reached the promise and use it as an opportunity to tell ourselves, well, why are we doing this? Which, trust me, I've had a number of people I've worked with who asked that question and then decided to go switch into a different field. I have lived every day for the last decade trying to make this a reality, and I believe wholeheartedly, and every day I believe it more, that the promise is possible. That we can make exoskeletons that can go into people's lives, that when you leave the hospital, they go with you, that when you show up in work and you're in a strenuous situation, you put it on because it protects your body, and it puts you in a place where for a few $1,000s and a few pounds, you are able to have better worker retention, lower workman's comp, things like that, and then ultimately into the home environment. I, not facetiously at all, hope one day you go into a Foot Locker and you buy a shoe that helps you run 25% faster. These things are possible. We're not there yet, but the pipelines are being created to make them happen. Thanks.